Good morning, everybody. I'm not going to ask if you're ready for a ladder problem because nobody is. Um, but it's going to be one of those days where we kind of do a single problem, right? Just because there's so much that sort of crops up. We really are applying all of the skills that we have learned in this class. Now, when I say that, I don't mean all the toolboxes, right? This is still very much like a Newton's second law, forces and torques. It's just we're using all of this problem solving skill that we've been trying to develop all semester to really get into the nitty gritties of what's going on in the problem. And so we want to make sure that we take the time together here to go through step by step. And I really encourage you to concentrate on the method, right? The ideas that I'm expressing, I'm going to teach you today, not just the specifics of the problem. Like every ladder problem is more or less the same. There might be little changes here and there that you have to apply, but if you're following the method, right, then you're going to have an easier time of it. So the method starts with, what's the first step? Visualize, right? Try to get your information organized. Ideally, there's a picture, but again, I didn't include a picture for reasons. And let's see, I think I kind of like to draw for whatever reason, I kind of like to draw my ladders sort of like this. Now, again, don't ever put a ladder like at this angle unless you have to, right? Okay. So what do we know? So this ladder is leaning up against this wall here, right? Okay. And this is the ground. So those are all like solid surfaces. Okay. Where's the painter? 3/4 of the way sort of up, right? So there's the painter, roughly 3/4 of the way up, right? And let's see. Now we've got the angle. We've got some, notice what they're giving us here. When they talk about the ladder and the painter, what are those? They're measured in newtons, so they must be what? They're forces. What force specifically? It's like mg together, right? It's not the mass. You don't have to take 650 and multiply it by g. They've already done that for us, right? So what in this visualization, right? I taught you on Tuesday that what we want to do is identify the central thing in the problem. What I refer to as the central actor, but it's really the object that ties all the other objects together. This will be the object that is common to all objects. For example, the painter is not it because the painter is not in contact with the wall. It's not interacting with the wall, right? So we've got a wall, we've got the ground, we've got the painter, we've got the earth. What's the thing in this problem that is being influenced by all those things? It's the ladder, right? So Tuesday's problem was the horizontal beam, right? And I kind of think of it as beam problems, right? I just got something horizontal, it's the central actor. Here, the ladder is our central actor because it touches the floor, it touches the wall, it touches the painter, it's being pulled on by the earth. It's the central thing. It's a beam, it's just at an angle, right? So we'll see what happens with all of that. So what was the sort of like, I don't know, visualization trick that I taught you on Tuesday to kind of make sure you get all of the interactions, all of the forces in the problem? You remember? Circle it, right? Pretend like you're a miniature person walking around the entire perimeter of the ladder, or you're an ant or a bug or something. You're just walking around the perimeter. Where do you want to start? The wall or the ground? The wall? Great. All right, so start at the wall. It doesn't matter. Just start wherever you want, okay? So at the wall, like sort of looking at this point right here, okay, we ask ourselves, right, like what are the forces at this point? We're in contact, so what do you automatically know about like a force of contact? There's going to be some kind of normal force, right? So here's our ladder, right? It's leaning up against this frictionless wall, right? It's in contact here. What direction will this force be if it's a normal force? perpendicular surface of contact, right? So I'm going to go ahead and I'm going to call that, I'm just going to call it W for wall. Again, it's a little bit bad because weight sometimes is W, but like, I'm just going to call that the wall force. I know it's a normal force. I know it's normal, and I could call it a normal force. I could call it like N1 if I wanted to, right? You could label it however you want to make sense for you. Whatever you want to do, yeah. Okay? Hopefully this has meaning for you, but when I put W, what I mean is wall, the wall normal force. Okay, are there any others? We sort of got tripped up yesterday with the horizontal beam, right? Where it came into contact with the wall and we discovered that we needed another one, right? That sort of that friction or whatever. Do we have any friction at the wall? No. What does it say? Frictionless wall. And you're like, that's stupid, Mr. Baylor. There's no such, walls aren't frictionless. You're right, okay? Most walls aren't frictionless unless they're icy or something, right? Why are we saying this wall is frictionless? Why do we always do this in physics? It's easier. Okay, right? You now know that if we put in friction into any problem, it can go bad fast, right? And there is friction in this problem. It's just not at the wall. So it's like one less thing to worry about. However, you do have friction in this wall, right? Do you have an inkling as to maybe what direction the friction might be? Is it pointing up or pointing down? What do you think? Like, what does the ladder want to do? It wants to slide down, right? Okay. So how is the wall preventing the top of the ladder from sliding down? By acting friction up, right? And what kind of friction is it? It's better be static friction, right? Okay. This is called statics, right? Static equilibrium. So if there were friction there, more than likely it would be pointing up, but there's not. Okay. So we keep going around. So we're starting at the wall. We're going to come down this side of the ladder, right? What do we run into? The painter, right? So what direction is the painter exerting a force on the ladder? Yeah, like downward, right? Like, and so gravity's pulling on the painter's being pulled down by the earth, but the ladder is supporting the painter. We're not drawing the force on the painter, we're drawing the force on the ladder. And so I would just come in here and I would say, okay, I'm going to draw this force down. I'm just going to call it P for painter. The painter's weight, right? And the reason I'm doing that instead of like mass of the painter times little g is because, again, in this problem, I was given the force, right? P is 650 newtons, right? Okay. We continue walking around the ladder, coming down. What happens here when we get to the floor? There is a normal force. So which way is the normal force? Directly up, perpendicular surface contact. And this is why I didn't call the wall force like N. I didn't use symbol N, right? Because I was kind of looking ahead and I saw, I'm going to have one at the floor, right? We tend to think of the normal force as like where the floor is or support structure, that kind of stuff. Okay, what else? Okay, there is friction here, right? But the question is, what direction is the friction pointing? Okay, there's different ways to go about doing this, right? You can go get on a ladder and you can experiment. Don't do it that way. You can get hurt, right? Okay. But which way does the ladder want to go? It kind of wants to fall out this way, right? Okay. And so the ladder, right, is pushing down and which way on the floor? Away from the wall, right? So the ladder pushes down and away. What's the reaction, the Newton's third law to that? Down and away. Up and towards, right? Well, we already drew the up force. What's the up force? It's the normal force. So what's the towards force? It has to be the friction. So that's one way, right? to kind of think about that. Here's a different way. As I'm looking, right, as I'm going to, I'm looking at all the forces I've got. I've got the wall, I've got the normal, I've got the painter. We haven't included one of them, the ladder, the weight of the ladder. We'll get to that in a second. Do we know, like in the sort of next step or the next idea that we're going to go for is that we are going to add up all of our forces in both the x and y direction, set them equal to 0. We're also going to do the same thing for the torque, right? So do we have 0 net force in the diagram right now? No. Where's the problem? The wall force has not been countered, right? We've got normal force up and painter force down, so there's the possibility in the y direction for 0 net force. But as we've drawn the picture right now, okay, there is no oppositional force to the wall force, which would lead me to conclude, since I don't have any other sources of horizontal forces, that my friction would have to be pointing towards the wall. It's very easy to get tripped up here. It's very easy, like the mistake you will make, right, is, and I won't ask for hands, but like, I know a lot of you just want to draw the friction that way, right? Okay. Now, what is this force? That's the force on the ground from the ladder, right? It's very kind of easy to think, okay, I've got this ladder, right? And the ladder's pushing that way on the ground. And so you draw that force. We're not drawing the free body diagram of the ground. What are we drawing? The ladder. So think Newton's third law now, right? If the ladder pushes away on the ground, then according to the song, the ground pushes towards on the ladder, right? So just be careful. Question every force you draw on the diagram. Be able to identify the object that's causing it and make sure that you're drawing like the force on the ladder, not the force on the ground or the force on the wall or any of that kind of stuff. Because up here at the wall, which way is the ladder exerting a force on the wall? In, right? We don't draw that force. It's there. We don't care about it because we're only drawing forces that are acting on the ladder. So if the ladder pushes in on the wall, which way does the wall push? Out, right? Newton's third law. Okay, so again, kind of two different ways to think about it, but they get you to the same position, which is the friction acting on the ladder is towards the wall. So when somebody puts their foot at the base of the ladder to steady it, what are they now doing? They're providing a force which way? Towards the wall, right? Increasing the safety margin, keeping the ladder from slipping out. Okay, we've forgotten a force. It's easy to forget when you're walking around the ladder like a little bug. It's the weight of the ladder itself, right? Okay, the earth pulling on it, because it's like the earth isn't attached, so to speak. So they don't tell me anything about the ladder, like where its center of mass might be. So if they don't tell me anything, where do I assume it is? At the middle, right? So I'm just going to go, I'm going to go ahead and draw. I'll just keep going. There we go. Ladder. I'm kind of making these a little bit long so that they're a little bit clearer. Maybe this isn't clear. I don't know. Okay. So by using the technique of like walking around the perimeter, applying what I know about like Newton's third law, I've tried to identify all the things that are pushing or pulling on my central object, my ladder. Now that I've kind of got that, and I reserve the right to go back and fix things later, right? It's not a step and it's done and you check it off and you ignore it for the rest of the problem, right? It's a flow, right? You might have to flow back to this and make some changes and then change your equation. So now that I've got the forces labeled, what else do I need to like be able to get any traction in the problem? coordinate systems, right? This is really important. Which way is positive, which way is negative? So we're looking at this thing, and I'm seeing a lot of forces that are lining up in a very specific set of directions. So what do you think we might want to do for our coordinate system? What are we going to call positive x? What are we going to call positive y? Up and down, lefty, righty, like horizontal and vertical. I don't see any components of forces that I need to find, right? I don't want to tilt my coordinate system with the ladder surface, because if I did that, I'd have to find like components of everything, right? All forces that I've drawn right here naturally are either horizontal or vertical, aren't they? So that I'm just going to go with like what's easy, right? What's easy here is that if I say positive y is up and to the right is positive x, boom, right? Everything is x or y, which is great. Don't have to find components of these forces at all. And you're like, Mr. Bailey, you told me ladder problems are going to be hard and that I should be afraid of them and all that kind of stuff. This is fine. I have no components. My life is good. I haven't said anything about torque yet. Okay, so let's, now that we've got our coordinate system here, right, and we haven't done any torques yet, should we just draw the linear, do Newton's second law linear terms? Just kind of get it out of the way. So, what does the template look like here? How many directions do we have? It's two, right? We have an x and a y direction, right? So x, y, they both start with 0 equals. That's nice, okay? And we'll get to torques later. Okay, so x direction. Let's see. How many forces? I see two forces, right? This is a horizontal force and this is a horizontal force. Which one of them is positive? Looks like friction is, and the wall force is negative, right? Maybe you're at a point now where you can like do that all in one line, right? You do the direction and the symbol at the same time. That's fine. I like to break it up. If I don't break it up, I tend to make mistakes. Okay. All right. So what are my vertical forces? Got L, P, N, right? So let's see. L. What sign do I put on it? Negative sign. P. N. Better be positive. Oh, yeah, sure is putting up, right? Okay. So here I'm looking at this, and sort of the little check that I do is, can I get 0, right? Have I written down a mathematical statement where 0 is possible? F minus W, is it possible to get 0? Yeah, we got, plus and minus. Negative L, negative P plus N, is it possible to get 0? So I may have missed something, but at least it's possible now, right? I haven't screwed up so badly, right, that I've got like F plus W, right, equals 0. That doesn't work. Okay, so those are buttoned up for now, and we'll come back to them in a second, right? Torque. Torque's evil, isn't it? Forces were evil back in the day. I remember the looks on you guys' faces when we were chapters 5 and 6, right? And now you're kind of like, oh, okay, that looks easy compared to torque, right? So torque is bad because it forces us to think in circles, and we're not as used to thinking in circles as we are thinking Cartesian, right? But try not to be afraid of it, right? Try to get used to this idea of clockwise and counterclockwise rotations. Put out of your mind all of that cross-producty stuff that we showed you. We don't really use that here. It's a good skill to have, and you're going to need it for physics 4B and 4C, right? Which is why we introduce it to you in 4A. But really, when the rubber meets the road in problems like this, and we're talking about torques, it's really just clockwise or counterclockwise. But we also, clockwise and counterclockwise don't really mean anything unless we specify an axis of rotation, right? Now, should this ladder be rotating at all? No, that's the whole point of this problem, right? But there are different places where we could like think of an axis of rotation? Where's one place where it like might naturally feel like we could put an axis of if the ladder were to rotate? At the floor, right? Okay. What would that axis look like, right? Well, it would look like something like this, wouldn't it? Right? Where that point is just, locked down and I can rotate the ladder about it. I don't want that to happen, but it's possible. Where's another place? The top, right? That would look like, that would look like this, wouldn't it? It's not supposed to move up. Here, more friction, okay? Right? So that would look like a rotation like that, right? I know you guys want to see it. But what's the other axis point? In the middle. Right? Going around the middle like that, right? Okay, but yeah. So, and I mean, I could put it anywhere, right? I could put the axis over here. That would be really stupid. Okay, right? Because now it's really complicated. I could put the axis on the moon. But we do have sort of I gave you a rule of thumb about where to put an axis if you just don't know and you're just guessing, right? This is better than guessing, right? Where do you put your axis? Where you have the greatest number of unknown forces acting, right? So what do we not know here? We don't know W. We don't know N, and we don't know L and P are both known, right? They gave us those numbers, right? So even just like I don't want to know what they want, I know I'm going to put an axis where? At the floor. Why am I going to put it at the floor? There's two unknown forces right there, N and P. And again, this rule of thumb makes the math simpler because when we write down our torque equation, we're not going to have like the maximum number of unknowns in that equation. We want to minimize the number of unknowns in equations if we can, because that makes doing the math easier later. So this rule of thumb doesn't save you, the setup is still hard, okay? But it saves you math further on down the line. So if you are just simply guessing, don't guess, right? Choose the location of the greatest number of unknowns. Okay, get rid of that. Stroke erase. There we go. Let's get rid of that. There we go. So this is where my axis is going to be. I think let's do all this in green. Go away. Nope, I'm not going to do it, huh? All right, fine. Okay. Now that we have identified our axis, we should specify which way we're going to call positive. And again, it doesn't matter which way you pick, clockwise or counterclockwise. What do you want? Counterclockwise? Why not? So we're going to define counterclockwise as being positive. With the axis in place and the definition of counterclockwise being positive, now I can write down torques. Students will come to me and say, Mr. Balogh, I don't know how to write down a torque. And I'm like, okay, well, show me your setup, show me your diagram. There's no axis, there's no direction specified. If there's no axis and no direction, I can't define a torque. I can't help, right? You've got to do these steps first so that writing down torque makes sense. So with that axis in place, does the normal force exert a torque? No, why not? The distance is 0. And what about friction? Also distance of 0, isn't it? So normal force and the friction are not going to come into play in this problem, in this section, right, where we're writing down torques. What I would like you to do is in pairs or small groups or something like that, I want you to spend the next couple of minutes writing down the torques over here. Do yourself a favor and just identify the torques themselves. Don't go like into the weeds and figure out R perpendicular to F. I just want you to get the directions on the things that are causing torques, right? So just do that together. Talk about it. Don't sit there in silence and do it yourself. Really just say, okay, start with L, then go to P, then go to W, identify whether they're positive or negative, that sort of thing. Go. All right, what'd you come up with? Torque due to the ladder, positive or negative? Oh, I don't, doesn't sound very certain. Positive? Negative? How many of you say it's positive? I know there's at least one. How many of you say it's negative? Okay, a lot of people go negative, so sorry, Jesse, you got overruled. That doesn't necessarily mean you're wrong, but you did get overruled. Okay, so why negative? How'd you figure it out? What'd you do? Okay, so hands or pencils or something, right? So I've got my ladder, right? Okay, and I'm holding up my pencil. I hold my pencil at the bottom where I said my axis is, and then what do I do for the ladder force? Either push it or pull it down, right? In that action, which way does the pencil rotate? It rotates clockwise. I'll do it over here on this screen, right? I'm holding my pencil like my ladder, holding it down here at the axis. The weight of the ladder pulling down on it would cause a rotation in the clockwise direction. And what did we say about clockwise? What direction is it? It's negative. So we put a negative sign on there. And so again, like, I've got a whole ladder here, but your pencil is a ladder. Your pencil is a beam, right? It's a tool you've got here right in your hand. But again, if we kind of visualize this, right, the axis is down there, and what is the weight of the ladder doing? I did that backwards for you guys. It looked perfectly fine for me. Okay, so the weight of the ladder, gravity's pulling on it right here. If that's the axis, right, we fix that in, and we just let gravity only do the work on the ladder, what happens? There's a torque there, right? The force of gravity is causing a torque, and that torque is the rotation of the ladder down that way in the clockwise direction. What did we say about clockwise? Negative. Okay. What about the painter? Same. So we can hold up our pencil, right? Pull down on our painter, right? We can even hold it 3/4 of the way up, pull down, but the direction of the torque still is same direction as the torque of the ladder, which means it's also negative. I'm getting really worried now, right? Because now I've got my ladder, okay, and I've got my wall force. I'm worried because I got two negatives. I better get a positive, right? But don't just automatically just write down positive and say, okay, I got 0. Check it, make sure, right? So, which way is the wall acting? It's to the left, isn't it? Which, when I push on this, causes it to do what? Go around counterclockwise. So counterclockwise is positive. All right. So kind of, we've done torques before. We did them in chapters 10 and 11, right? And I showed you the pencil thing. This is like the second or third time we're doing this. The new parts, right, are thinking about adding all the torques up to 0, checking that. And here's another new thing for you, okay? It's the choose a different axis to make sure that you get 0 still. Remember how yesterday I deliberately made a mistake to point out that following the procedure can save you, can point out where maybe you made a mistake with your forces? This is one of those checks that you want to do. So we're down in step 4, right? Visualize, strategize, do it, check it. We're strategizing, we're trying to write down equations now, but we're going to quickly jump to the check it step. And so what you want to do, we picked an axis down here at the bottom of our pencil, our ladder. So we want to pick a different axis. What's the other axis I'm going to pick? The one at the top, okay? And now I'm not going to write any math down. I'm just going to check to make sure that I can get 0 torque from this point as well. If I can't, there's probably something I've missed. If I can, I might be okay. Doesn't guarantee like 100%, but 95% we've got everything. Okay, so with the axis up here, let's do the normal force, okay? Which way is normal force pointing on the ladder? Up, and it causes a counterclockwise rotation, right? Okay, what about the friction? Oh, made it go the other way, right? So is it possible to get 0 net torque if I've got one making it go counterclockwise and clockwise? The way around? Okay, yes. So I did a check there, right? I could do the ladder and the painter, they're both, right? Okay, but the point is I do have an opposition of torque, so it's possible. Yesterday we ran into a problem that we discovered when we went to the other end of the beam, that we couldn't get 0 net torque, which told us that we had missed something about the wall force, and we had to go in and put a component there, so on and so forth. So here we're okay, right? Or at least as okay as we can be to this point, because it's the next part that's going to wreck your brain. You're like, Mr. Balogh, my brain's already wrecked. All right, I haven't showed you anything new yet, right? I know we did it on Tuesday, so it's fairly new in that sense, but up to this point, I've repeated the process that we've done. And I'm about to do something you've already seen, but it's going to be weird because of the ladder. What's the next step I have to do? You know what the step is. What do? You've got to do that R perpendicular to F thing, right? You've got to find a distance, and you got to find a force. What must that distance and that force be with respect to each other? Perpendicular. No? The terror in your eyes is not there, so you don't see it. Okay, so somebody. So I think the thing I'm actually going to do this 2 different ways, okay? And this is part of the confusion, but it's important that you understand and know and see the 2 different ways you can go about thinking about this. So let's do the torque on L first, right here, okay? So I'm actually, so let me do this. I'm actually going to just pull the ladder out all by itself, and I'm going to draw my L force right here, okay? I just want to sort of, this diagram is getting confusing enough already. We just want to concentrate on what's going on right here. So my axis is down here. Where's R? Like, what is R? In that statement of, we write a torque as R perpendicular to F. Where's R? It starts where? At the axis and goes where? It goes like to the, that's confusing too. So I'm going to draw R like that, right? I mean, technically it's a vector. You'll use that more in 4B and 4C. But there's my distance, right? It goes from the point where I've defined my axis to where the force is acting. Is that R and that force L perpendicular to each other? No. We can't write down a torque unless we can write down the right? We need it. We need the two things at 90 degrees to each other. So now we have a choice. We can find the perpendicular component of force to that distance, or we can find the perpendicular distance to that force. Spoiler alert, you're going to get the same answer regardless of how you think about it. So let me back up. Let's find the perpendicular component of force, because I think that's the one you're going to be more comfortable with because we've done this a lot. What is the direction that is perpendicular to R? Mr. Balogh, like, it's perpendicular to R. What are you asking? I'm going to draw the perpendicular to R right there at that point where L is happening, right? So do you agree that that's a 90-degree angle with respect to R? Okay. We need the component of L that is along that dotted line. What does this kind of feel like? Back when we did a hill and a box on a hill or whatever, a penguin in a crate on a hill, whatever it was, right? Okay, we did this, didn't we? At that point, we had a tilted coordinate system, didn't we? Right? Well, we're not doing the red. We're not doing Newton's second law. We're doing torques. We're doing second law in rotational terms. We're doing a torque here now, right? And what we need to find is a perpendicular component to the distance. And it happens to line up such that if L were like the hypotenuse of a triangle with components that are kind of doing that, right? Forming that right triangle down there. And we know the angle. They've given us this angle. Can you tell me what that angle is? It's theta. We've been here before, right? Okay. Again, it's feeling a lot like the hill problem, right? Where we drew the normal, we have the weight, and then we kind of went like that, and we just kind of knew already from geometry that that was going to be that, right? Okay. So that's what I'm like carrying over and asking you to kind of remember. So if that's the angle and L's the hypotenuse, what is the component of L that is perpendicular to R, sine or cosine? Cosine. Why was it cosine? It's touching the angle. Yeah. Yeah, the other one was flat. And so we just broke up T into X and Y components, right? Away we go. Here, we need to, because with the last example, which is duh, right here, okay? Here's our angle theta, right? Here's the thing that's perpendicular, and here our R was right there, wasn't it? The R was nice and horizontal, and so we needed the perpendicular piece, right? Yeah, don't just automatically assume the perpendicular one's always going to be sine or always going to be cosine. It totally depends on the problem and where the angles are, right? Here, we have an R, and we need to find a perpendicular component of force. Same thing as that perpendicular component of force in the last problem. It's just, it's harder to kind of maybe see it on the ladder because of the angles and things. Okay, so now that we know the perpendicular component of the force, how do we write down the torque? What's the distance? What is R? It's half the ladder, right? So the distance is L over 2. And then, so it's R, we wrote down R, L over 2, times the force. What's the force? L cosine theta. Okay, we're going to do it again, but we're going to do it with the painter. Now, with the painter, I can draw sort of a separate, like, quick little ladder. I can draw just the painter acting down, right? I know my axis is down at the bottom. What's this distance going to be? 3/4 the ladder. 3/4 the ladder. That's supposed to be a terrible 4. Yeah, I should be fired. How would that be, having your teacher fired 3 weeks before your last exam? Awful. All right. Yeah? Is that the solution? Pass everybody? That's called high school. All right. So there's the angle. What's this? It's the same. That's not a question, right? So what does that make the perpendicular component of the force perpendicular to the 3/4 L? P cosine theta. So what am I going to write up here? 3/4 L, that's the distance. What's the force? P cosine theta, right? This is R perpendicular F. This is R perpendicular F, right? That I'm writing down in there. Okay. Oh, geez, I ran out of wall. Plus, oh boy. Now, okay, so redraw the ladder, make it nice and clean. These are just quick sketches. They don't have to be really, really like perfect or technical or anything. There's my wall force, right? Okay. Where's the length? Where's R? It's the entire ladder, isn't it? So there's our L. We know that the direction that is perpendicular to L is that one, which means that we need the component of W that's pointing up that way. So W points like that and then like that. Those would be the components of W, but we don't need the one along the ladder. We want the one that's perpendicular to the length. What angle is that? Before, we kind of, like this is familiar territory, right? We have a geometry like this. We kind of go, oh, I know what that angle is. We're done, right? We're not in familiar territory, right? So we got to fall back to geometry. So not only are torques like kind of difficult to sort of conceptualize and understand and write down, now I've got to do some geometry, Mr. Balogh? The answer is yes. So let's see. Alternate interior angles are equal. Means that has to be theta. Two parallel lines bisected by another line. The angles that are alternate and interior, alternate and interior. So I've got two parallel lines and I've got another one that goes through, okay? The rule is that angle and that angle will be the same, okay? So that's that angle, and I could stop here because what can I see about this component? It's not touching, so what do I use? Sine. I know your brains have given up. I know your brains have kind of given up, and you're like, you know what? I'll just watch this later, and hopefully it'll make sense. Try to be present here, right? Don't give up. I'm going to give you another way to think about this, and I hope that gets your brain sort of feeling comfortable about one way or the other. I'll explain what I mean there in a second, okay? But right now, we've identified the component of W that is perpendicular to that distance right there. So what are we going to write down for the torque? What's the distance? What's R? It's L. What's the force? W sine theta. Okay. So that way of seeing torques, where you take the distance from your axis to where the force is and then find the component of force that you need, is one way to do this. I want to show you the other way, and I've already kind of showed you this idea once already when I first introduced torques to you. And I drew a picture of like opening the door. I said you can think about the perpendicular component of force, or you can think about the distance that is perpendicular to the force. This method has lots of names. I like to call it the line of action method. That's kind of what some engineers I know refer to it as. It's a different way of seeing exactly the same thing. And so what I'm going to do is I'm actually going to do it on a different page. Okay? This is either going to confuse you more, or your brain's going to go, oh my gosh, now I see it, or now I understand. If it confuses you more, just do it this way. Okay? But if this way helps you, excellent. I will preface this by saying I have looked at technical diagram. I had a engineer come to my house one year because I was going to put solar panels on the house, and they needed to do an engineering analysis to make sure that my roof was going to hold up the weight of the roof and the solar panels. And so as part of the project, it was required, had to have a licensed engineer come out and look at all the trusses in my roof and determine whether or not it was structurally sound. And so he came out and he crawled all through my attic and he made measurements and he went away and he made drawings, and I'm sure he used a computer and all that kind of stuff, right? But in some of the drawings, he was showing, as part of the method, you had to show the method. Not just that the computer did it, but that here is the engineering static diagrams of like a sample member and all that kind of stuff. And as I went through the report and I started looking at the technical diagram, I noticed that this engineer was mixing both of these methods on the same page. The method I'm about to teach you, the line of action method, and the one I just taught you, the find perpendicular components. And when the engineer came to meet with me to go over the analysis, I started asking him very pointed questions about it. Like, why did you do it? He's like, what do you do for a living? I was like, I teach physics. He's like, oh. And he's like, yeah, I didn't really like my physics classes. I don't blame you for that. I get a lot of hate in my life. It's okay, right? Okay. But I really, for my students, I need to know. And then he was like, oh, it was for your student. Okay, let's talk about it, right? And so I asked him, I was like, why did you do it this way? And he's like, why wouldn't I do it that way? Like, not only was I taught to do it this way, but I have a tool in my toolbox. Why wouldn't I? So he was using the line of action method when it kind of made sense to him in the diagram to do it that way. And then he used the component of force method when it was easier to see it that way. Like, both of these tools give you the same answer. It's just a different way of sort of conceptualizing it. And I was flipping through the pages, and I remarked to him, I was like, I know how to do this. This is all vectors and components. I could have done this. Why am I paying you to do this? He just smiled and said, he said, well, do you have a license? I was like, no. He's like, where's my money? Right? So, yeah, just because I know how to do it doesn't mean I'm good at it or have a license to do it. I have a license to teach you. Actually, I don't. I have no. That's my license, my faculty ID. State of California says that if you have a master's degree in the area of expertise, then apparently you have a license to teach. You know how many teaching classes I actually had to take, like, on how to be a teacher for my physics master's degree? This explains why there's a lot of bad physics teachers. They're probably good physicists. Do you know how many classes I took on education for my master's degree? Because I went over to the education department. I was like, what do you guys teach? And they're like, how to make kids be happy with bananas in the classroom. And I was like, I'm out. Right? So I went and started doing physics education research. I wrote 2 master's theses, one on extreme ultraviolet optics and the other one on the andragogy of physics. Andragogy is a very fancy word for how do adults learn. Have you heard of pedagogy? Like how kids learn? Andragogy is the correct term for you guys because you're adults. Apparently your brains are no longer plastic or something. I don't know. No, your brains still are. Okay, that was a break. That was a tangential break to reset your brain. What are we going to do? We're going to do the same problem. We've got our ladder. We've got the gravitational force of the ladder acting down. We know our axis is right here. But in this method, I am going to leave the force alone. I'm not going to find components of the force. I'm going to find the distance that is perpendicular to this force. The line of action of L is vertical. L is acting along a vertical line. What direction is perpendicular to vertical? Horizontal. So I need the distance, the horizontal distance from my axis. Here's my angle. What is the distance like up the ladder? Like the hypotenuse. So I now have a right triangle, right? And I need a hypotenuse. What's the hypotenuse of this triangle? Half of L, right? We're the distance from here. I drew those arrows wrong. This distance is 1/2 L. That's the hypotenuse of my triangle. I need the distance that is touching the angle. L over 2 cosine theta. So now, when I write down the torque for this, what distance do I put in? L over 2 cosine theta times, and what's the force? L. And what did we just get? Exactly the same thing, right? I didn't put the negative sign on because I'm not putting in the torque equation, right? But I got the cosine theta, I got the L over 2, right? It's all sitting right there, and it's exactly the same torque. It's just instead of thinking about and finding a perpendicular component to the force, what I did is I said, okay, leave the force alone, find the perpendicular distance. So let's do it for P. What does P look like? So here's the ladder, here's the P force, right? If I was 6, that would be really funny. What's the distance from the axis to the force? 3/4 L. That's going to be the hypotenuse of a triangle. The line of action of P, vertical or horizontal? It's a vertical line of action. What, therefore, is the direction that is perpendicular to vertical? It's horizontal. I'm going to find this distance right here. I know 3/4 L is my hypotenuse. I know my angle's right there. What's the answer? 3/4 L cosine theta. And then when I write down the torque for this one, what's the distance? R. 3/4 L cosine theta. That's the distance that is perpendicular to the force P. Mathematically identical. All right. I think this is where this one really comes into its own. Remember how we kind of struggled with W a little bit? We had to do some geometry. Watch this. W's up here, right? What's the line of action of W? Well, first of all, how far away is W from the axis? It's L, right? It's all the way from there, right? Okay. What's the line of action of W? It's horizontal. What direction is perpendicular to a horizontal line? A vertical line. So that means I need this distance right here. This distance or this distance is the same distance, right? Okay. Hypotenuse is L, and I want the length, the side of the triangle that is not touching the angle. L sine theta. No complex geometry required. And now what's the torque going to be? What's the perpendicular distance? L sine theta. And then the force is W. And this is exactly the same as that right there. What's that?
I like it just because the drawings are cleaner.
Yeah, so for certain brains are going to look at this and go, oh my gosh, this is so much better. And other brains are going to go, ah! If your brain is doing that on both, I'll see you in grasp. Okay? Because, right? Which is perfectly fine. Doing that on both is where you should be at right now. Because you're, again, knowing is how you know stuff, and you're seeing this for the first time. So you got to go. You got to struggle. You got to think about these different methods, right? I would encourage you to practice as much as possible right now, right? Get used to these two different sort of ways of seeing a torque, especially if you're going into statics, because you're going to be seeing torques a lot. Again, they call them moments in engineering parlance, and I think it's because you're going to have a moment when you deal with them. So whether you see torque as a distance times a perpendicular component of force, like you break the force up into its components and find it that way, or you leave the force alone, line of action of force, and find the distance that is perpendicular to that line of action, what's going to happen? Your answers will be the same, right? And if you want to mix and match in a problem, be my guest. Sometimes finding a torque for a certain force, it's like it feels easier or natural to do the component of force way. But for another one, it feels like it's easier to see if you do the line of action. You can mix and match in the same problem. It doesn't make any difference. It really is kind of a powerful way of being able to deal with all this. All right. It is 8:57. We started at 8:01. What haven't we done yet? Any math, right? This has all been set up. How long are problems going to take in chapter 12 if ChatGPT isn't doing it for you? Oh, by the way, not that I would recommend using Google Gemini, but Google Gemini is currently free for all students, anybody basically that has a .edu email address, right? So, and it unlocks like all the premium features of Google Gemini, whatever that is, okay? So I would recommend take advantage of these freebies. They'll probably want to start charging you, but it's next year, or they're giving you Google Gemini free for a year. ChatGPT or OpenAI felt left out, and so yesterday they announced access to their premium, like all their fast models and all that kind of stuff for free for students for 1 month. Okay? After which, to do it, they'll want to charge you. So for the next month, you can get ChatGPT for free, right? Of course, they want you to get used to using it so that when you go to your employer or whatever, you say, all of you came out of a school program where you had like Chromebooks and Google Docs and all that kind of stuff. None of you know how to use Microsoft Office, right? Okay. Which Google won, right? They've got a generation that is just used to Google products, right? The AI war for education space has begun. I was just waiting for it to happen. I was like, give me the free ones, right? Because I know it's going to happen, right? And it's here now, right? So Google Gemini, I've noticed, is not very good at math. Okay. Search, so not surprisingly, it's pretty good at. Math, not so good. ChatGPT, really good at math, physics in particular. And then with the newer models, not the older ones. And then you might not realize this already, but you have full access to Copilot, which is Microsoft's version, which is built on ChatGPT. ChatGPT and Copilot are the same backend. And you have access to that through your student email. Like you can get like all of Microsoft Office for free, and that includes Copilot and all that kind of stuff. So take advantage of it, and that's as long as you are a student in this district. And then wherever you transfer to, I guarantee you that they've got free access to things at the other schools, right? Oh, and wasn't it the state, California State University system said they partnered with Anthropic? And so Claude is now free for anybody that's at a CSU. And ChatGPT just, it's the other way around. ChatGPT did the CSUs. Anthropic partnered with Instructure, who makes Canvas. That is not yet free for everybody that uses Canvas, but I'm sure it's coming, right? So get used to using multiple AI agents. Just like my kids had to get used to using Microsoft Word and Google Docs until Google took over, right? You guys are in the age of having to work with multiple. Boy, that was a tangent. All right. We have some math to do. I don't even remember what we're doing anymore. What are they asking us to do? Find the coefficient of friction. Where's the coefficient of friction? Oh, this has not been fun, Mr. Balogh. Fun. Okay. So walk me through a strategy before we start doing any math. How am I going to find this coefficient? What do I need to find? I need to find F and the normal force. How am I going to find the normal force? It's right there, isn't it? The normal force is the only unknown in that statement because L and P are both numbers, aren't they? Okay. How am I going to find F? The only place it shows up is right here, right? So F is equal to W. Whatever W, how am I going to find W? It's right there, isn't it? This is a number. That's a number. W is the only thing I know. So my strategy is solve for N, solve this for F, solve this for W, put that W right in there. I'll know F, right? So what does that look like? It looks like blue. F equals W. N is equal to L plus P. Like, I move the negative things over to the other side of the equal sign, they become positive. Over here in the torque equation, I'll rewrite it just to show you what's happening here. Minus 3/4 L P cosine theta plus L W sine theta. Okay, so they don't tell me the length of the ladder, right? But it's in every term. So it cancels. What's 1/2 L cosine theta? That wasn't a hard question. What is it? It's a number, right? How do I know it's a number? They've given me everything. They've given me L. They've given me theta. I know how to deal with 2's, right? So now if I move a negative number to the other side of the equal sign, what does it become? A positive number. So 1/2 L cosine theta. What's 3/4 P cosine theta? A number, whatever it is, okay? And then that leaves behind W sine theta. So what am I going to do to both sides? Well, I think I'm going to factor out a cosine theta first. 1/2 L plus 3/4 P. And then that's equal to W sine theta. And now what do I do to get the W all by itself? I divide by sine theta. And then what's cosine divided by sine? It's cotangent, isn't it? So cotangent theta, it's the first time that's shown up in this class. 1/2 L plus 3/4 P is W. And what is cotangent theta 1/2 L plus 3/4 P? It's a number, right, that I can figure out. Okay? So now that I know W, W is going to go into here. That's going to give me F, which goes in there. My N is known, which goes in there. This is doing math by arrows. I didn't even get my notes out. That's how ingrained this problem is in my brain. The horror of it. Oh my God. We're not doing fluids yet. You guys probably like fluids. Okay, let's see. Nope. Where's my ladder problem? Right there. I got 0.3. What are the units of the coefficient of friction? No units. What does this mean? What have we discovered? What have we found? If the coefficient between the ladder and the floor, say, is 0.5, what do we know? We're safe, right? Because if the coefficient is 0.5 and what we need is 0.3, We're golden, right? But what if the coefficient is 0.1? This is going to fall, right? The angle here. So notice that this full answer, I should have written it down somewhere down here, right? The F is the cotangent theta plus some numbers, 1/3 P, right? All divided by L plus P, right? This is what mu is. It's a function of the angle, right? So what's safer here? So cotangent's kind of weird. Let's see, the tangent of 0 is 0, isn't it? But the cotangent of 0 is like infinite or something like that? Yeah, because it's the inverse of the tangent, right? So in order to have this be as small, the coefficient to be as small as possible. And why would we want well, let's think about it. Let's go this way about it. What happens if the angle is 90 degrees? What's the cotangent of 90? It's cosine divided by sine. So what's the cosine of 90? 0. And what's the sine of 90? 1. And so what's 0 divided by 1? 0, right? So a perfectly vertical ladder needs no friction to stand up. I believe it, right? Okay. But what happens as we make the angle bigger and bigger and bigger? What do we need the coefficient to be? Bigger and bigger and bigger and bigger, right? Okay. Until it gets infinitely large when we lay the ladder down, right? So that's sort of the function of the dependence, and it kind of makes sense, right? The more vertical your ladder is, the more forces going into the ground, right? As opposed to along the ground, which is why you want a ladder to be mostly vertical. Again, climbing a vertical ladder, woo, right? Not very smart, okay? You want some angle there so that gravity is pulling you which way? Towards the ladder, right? Okay, so we discovered the statics of ladders. So you're like, Mr. Balogh, the world has known about them for millions of years, hundreds of thousands of years. Okay, there is a problem. Before I let you go, I want to show you something. That's 4B. You don't want to see 4B problems. 4A problems. Assignments. What chapter? Chapter 12. 32 of you have not started. Repent. Get started. Grasp, yeah, grasping at straws. All right, so let's go student view. All right, so I was a little bit nervous there. I thought maybe it wasn't going to work. Where is it? I didn't go right to it. Right there. Okay, so where's the wall? It's right here. Okay, right? This is the part of the ladder that is preventing me from falling that way, right? So the hint in the problem tells you to do what? Can you read it? It's kind of small. Isolate the two halves of the ladder, right? So there's a side here that I'm standing on, and then there's a side over here that's acting as a support, okay? Draw free body diagrams of each side of the ladder, right? So you can draw like my ladder like I did before, right? Okay, for this side, and then you're going to find this side. What's this right here? What is this doing? If this weren't here, what would happen? Right? So which way is the tension in this tie rod acting on my side of the ladder? Can only pull, right? Tensions can only pull, right? Which way is it pulling here? Okay. Now, it is a frictionless floor. So what does that mean about friction in the floor down there? There is none. But is there a normal force here on the bottom? Yes. Is there a normal force over there? Yes. Are they different? Yes. I'm standing on this side. I'm not standing on that side, right? So the normal forces there will be different. Think very carefully about what's going on at the top of the ladder. I gave you a clue or a hint that this side is acting like the wall. But this wall is not frictionless. There's no friction up here, to be clear. It's like a bolt, right? It's a piece that articulates, right? But think very clearly about how the two sides of the ladder interact with each other. And when you get stuck, go find a tutor. And when you're going to come up to them and you're going to say, I'm doing the ladder problem for Physics 4a, and they're going to go, okay, I can do this. Have a great rest of the day. I think I should lecture up here. What do you think? I feel tall. I'm taller than Randall, so I mean, it works. Have a great rest of the day. If you could get out of here quickly, my Physics 4B students are having an exam today, and I think they're scared. So hopefully, oh, I'm going to put up an announcement. I will not be in GRASP after 8:30 tomorrow, but the tutors will be there, okay?
So 0.3 coefficient.
I mean, unless you want to be on YouTube.